Hello, let's do a quick guide of the equation booklet that will be in the exam with you. The equation booklet contains a lot of useful information. So I'll be going through it, highlighting any laws using red pen, any definitions using green pen, any origins where needed, where the equations come from, literacy in pencil. I'll be highlighting energy using a pink highlighter. I'll be highlighting forces using a green highlighter, and some accelerations using a yellow highlighter. Let's start with the M6 module, Module 6, Particles and Medical Physics, and the first section is capacitance and capacitors. And the first thing we have is at the top here an equation C equals Q over V, C for capacitance, Q for charge, V for potential difference. And this is actually the definition of capacitance. And you would say that definition as capacitance is the charge stored per unit potential difference. Following that, you have a series of equations that allow you to calculate the capacitance of different types of capacitors. The first one is like the parallel plate, two plates separated by an insulating material, how to work out what the capacitance of that is depending on the area of the plates, the distance between the plates, and permittivity of free space, but there might not always be free space between the plates. So you could also have another material, so it could be rubber or something like that, in which case they'll give you a different permittivity. Or they might give you a relative permittivity, which means it's usually communicated with reference to the permittivity of free space. If this was a relative permittivity of 2, that just means 2 times the permittivity of free space. Just a little note here about permittivity, lowercase r, is the relative permittivity. And to work out what it actually is, you take a relative permittivity and times it by the permittivity of free space. The next equation below is designed for calculating the capacitance of like a sphere that can be loaded with charge. And the classic example of that, to dial it in, would be a Van de Graaff generator. The next equation is for adding capacitors in parallel. And this one would have an origin story. So over here I'm just going to quickly draw a parallel series of capacitors, create a visual context there, so that's related to this particular equation. And in order to achieve where this equation comes from in this circuit, we have a junction here, and we can apply Kirchhoff's first law. In a normal circuit, current in equals current out, sum of the currents into the junction equals sum of the currents out leaving the junction. But in this case, it's not really a current, it's charge. So whatever charge goes into that junction, that charge is going to have to leave that junction. So we would write Kirchhoff's first law in this application as Q going in equals Q1 going through capacitor 1 plus Q2 going through capacitor 2. We would then substitute in this equation up here. We would rearrange it and make Q the subject. Q equals C times V. So Q equals C times V, and Q1 would be C1 times V, and Q2 would be C2 times V. And because it's a parallel circuit, the potential difference is the same everywhere. So the V's cancel, leaving behind the rule for adding together capacitors in parallel. The next one down is a similar story, but it's capacitors in series. So I'll just quickly sketch out a couple of capacitors in series. Now if you get confused whether you're supposed to apply Kirchhoff's first or second, it's impossible to apply Kirchhoff's first in this circuit because there aren't any junctions. So I'm going to try and follow the same story as above. I'm going to apply Kirchhoff's second this time. And in Kirchhoff's second, you're going to be summing the EMFs. So in this particular case, we would say the EMF from the battery would equal the the potential difference across capacitor 1 plus the potential difference across capacitor 2. And then again we'll substitute in the definition of capacitance. We'd rearrange this to make V the subject, and we would end up with Q over C equal Q over C1 plus Q over C2. the total charge stored by both of these capacitors is the same as the individual charge stored by either of these capacitors. Long story short, everywhere in a series circuit the charge stored is going to be the same, so that allows us to cancel the charge, and that leaves behind the method with which we add capacitors in series. So this one moves up to there, and then we go down, and this one goes there, and then we move down. So we've got two origin stories right there, quite nicely. Next we have an assortment of equations where they've got W equals W equals W equals. That stands for work done, and work done is an energy, so I'm just going to highlight those in pink so they pop out. Any energy can be joined onto any other energy. This whole section here is for energy stored on a capacitor. The origins of all of these equations comes from this one right here, the one at the beginning, energy equals a half QV. So there's an origin story that's going to go with that. This represents the area under a graph, and that graph is the more charge you load onto the plates, the more potential difference you'll have across them, or the bigger the potential difference you put across the plates, the more charge you'll store upon them, with the gradient, straight line gradient like so. The inverse of the gradient of the line would be the value of the capacitance, and the area underneath this line, this area here, would be the energy, and that energy would be the area of a triangle, half times the base times the height. The rest of these energy equations are simply from substituting in the definition of capacitance into this equation to produce two other similar ones. And when in an exam, I always pick the one whose numbers I'm most sure about. So if I'm sure about the voltage, the potential difference and the capacitance, I'll choose this one. If I'm sure about the charge and the capacitance, I'll choose this one. Next we have a definition, and that definition would be for time constant, common definition you get asked. I'm going to write time constant, but usually they say time constant for a capacitor resistor circuit. And in order to explain what this part means, you've done all the studying behind the lessons. It is the time taken for the charge on a capacitor to fall to, I'll put 1 over E, but in brackets 37%, which is roughly about the same thing, of its initial value. And this would be true also the time taken for the potential difference on a capacitor to fall to 37% of its original value, or you could apply it to current, but traditionally put charge in there. And then we've got our charging and discharging equations. They've got X and X naught because this could be Q, Q naught, or V and V naught, or I and I naught, so this can be used for charge, potential difference, or for current. And then we've got something similar but with a 1 minus. So the shape of this particular graph would be worth illustrating in comparison to this one. Here we start from X naught, whatever it is, and we decay away from that as time passes. In this one we start from naught and we approach X naught. So you should be able to see by looking at the graphs where this 1 minus bit comes from. So we would use this equation for a charging a capacitor and having a look at the way the potential difference changes over time. We would also look at charging a capacitor and having a look at how the charge stored on it changes over time. For this one, we would use it for discharging and having a look at how the charge stored on the capacitors changes over time, discharging, and looking at how the potential difference across the plates changes over time, discharging, and looking at how the current flowing in the circuit changes over time. And the unusual part is also if we were charging a capacitor, we would also use this same equation to look at how the current changes over time for charging. So that's counterintuitive or unexpected or some such. So if I did a quick table here of charging and discharging and did a like for like comparison for looking at the charge over time, both sides, the potential difference changing over time for both sides, and the current changing over time for both sides. The discharging side is e to the minus t over rc, e to the minus t over rc, e to the minus t over rc. So there's a pattern there, and on the charging side you would use the 1 minus e to the minus t over rc, and then for potential difference 1 minus e to the minus t over RC. But then for current, none of this 1 minus stuff, it would decay the same as it would do if it were discharging, say, e to the minus t over RC. And that's pretty much all the equations you get given in the exam to do with capacitors.